let's get started. I want to check real quick. Can folks at the back hear me okay? Perfect. Well, welcome. Thanks for coming to the session. I'm glad you folks made it. We barely made it ourselves. We ended up being at the wrong room. But we are finally here. I think we had a little less coffee in the morning. Did everyone enjoy the party yesterday night? Yeah? Yeah, I did too. I actually broke my glasses, so they're kind of like stitched together right now. But if one of them like pops out, then yeah, I'm sorry about that. So yeah, we're going to talk about deep learning with PyTorch using Azure Machine Learning service today. And I'm Nishank. I am a PM with Azure ML.
And I'm Mina. I'm also a PM on Azure ML.
So before we walk through the agenda real quick, I just wanted to get like a show of hands on how well-versed are people with deep learning and data science in general, so that we can tailor the content accordingly. If you could just like raise your hands, we can tailor the session.
So if you are a data scientist or are pretty familiar with deep learning, cool.
Cool, perfect, okay. So yeah, just a quick overview of all that we are going to cover today. We're going to give you an overview of Azure-AI. We're going to talk about deep learning. We'll also tell you how you get started using an Azure Data Science Virtual machine. We're going to talk about distributed training in Azure, and then dive right into PyTorch. Then show you how you scale with Azure Machine Learning. Finally, do a demo on style transfer, and then summarize and take questions. This is like a 3-hour session, so we'll see how you folks hold up, okay? Okay, let's get started. So just a quick overview of Azure AI. I'm sure you folks have seen this slide before. We have primarily 3 pillars. We have apps and agents, which is all about conversational interfaces that you can build using pre-trained models. We have machine learning, which is the custom pillar for Azure AI. So you can bring in your own data, train your own custom models. And then we have knowledge mining, which is essentially about using a lot of data and getting rich insights out of it. So like pass in a bunch of images and it will be able to tell you exactly what kind of insights it is able to derive from that data. So today we are specifically going to focus on custom machine learning, which is the central pillar. It has 2 key offerings, the Azure Databricks and Azure Machine Learning, which previewed this week. Double-clicking, which is very Microsoft-y into this. So this is the entire gamut of services and platforms that we offer as part of machine learning on Azure. You can start with sophisticated pre-trained models. So you can use something like a vision or a speech model, bring in your own data, customize those models a little bit, and then start getting insights on that. We support popular frameworks like PyTorch and TensorFlow. And then there's Onyx. We're going to talk a little bit about that also in the session. We have productive services such as Databricks and Azure Machine Learning and machine learning VMs. These essentially allow you to play around with your data, create models, and then go deploy them so that you can start getting insights on your data itself. We have powerful infrastructure. We have GPUs. We got CPUs and FPGAs now. So we're going to talk a little bit about GPUs as well. And then you can easily deploy it either on-prem or in the cloud or in the edge. So this session, we're going to focus on 3 or 4 key things. We're going to show you how Azure is the best place for PyTorch using Azure Machine Learning and the GPU infrastructure that Azure provides.
Hi, so we're going to first go through a quick deep learning overview just to make sure we're all kind of on the same page. So what is deep learning? We get this question a lot. What's the difference between AI, machine learning, deep learning? Are they all the same thing? And they're often used interchangeably when getting written about in today's literature. So you can think about them as concentric circles, or in this case, rectangles. AI is the idea of having intelligent machines or getting computers to be more characteristic of human intelligence. Machine learning is a subset of AI that started around 1970s, and that's the development of statistical algorithms to actually learn from data. So if you think about the early spam filter detection in your email box, those are like applications of machine learning. Finally, in the past decade or so, deep learning has really exploded in popularity and been used in a lot of state-of-the-art models for a variety of applications. And so deep learning, these models are called deep neural networks, and They're really good at learning representations of data and identifying patterns. And this is just a subset of machine learning with a subset of algorithms.
And Meena, why did deep learning suddenly start only in the last few years?
Yeah, so before we had the idea of artificial neural networks, but these were much more shallow. And with the development of more powerful hardware and research, we've really seen it gain popularity in the past decade, especially starting with revolutionizing computer vision. So what are some deep learning applications? They're pretty much everywhere. You have language translation, so translating from English to French, for example, if you use Skype or Google Translate. Image recognition, so deep learning excels at a lot of image tasks, image classification, object detection, image captioning. We have speech recognition, so if you use Cortana, it automatically recognizes what you're saying. It can model what you're actually talking about. You can also synthesize text from speech. There's time series forecasting, predictive analytics, so if you want to make relationships between past and future events, look at things like hardware breakdowns, etc. Finally, autonomous vehicles, self-driving cars. Those use a lot of deep learning technology like object detection and image segmentation. So there are a ton of applications basically across all industries. So what is deep learning? You've probably heard of it as being described as a black box. We know what goes in and we know what comes out. It's mapping inputs to outputs. But this is something that even researchers can't really say. Like, we know what mathematics go behind building these models, but we don't know exactly why they work so well to state-of-the-art performance, or even better than humans in some cases. And this is because in deep learning, you can't really trace the prediction back to the specific set of features that really lit up that prediction. We'll talk about that in a couple of slides. So what are neural networks? They're loosely modeled after the human brain. At the highest level, a neural network is made up of a series of layers. And a layer basically takes an input and feeds out output. So you start with your training data set, and each subsequent layer takes the output of the previous one to learn more and more complex features. So the first few layers of a neural network, like in this case, this is for image work, you'd identify more low-level features, such as edges or blobs. You feed these into the mid-level features, which can pick up more discernible things like, parts of the face, the ears, the eyes. And finally, the high-level features towards the end, the last few layers, really can get a more complex representation. So this is what we call hierarchical feature learning. And so the model, as it goes deeper and trains through more of the inputs, gets a really good complex understanding of your training data set. And this is why neural networks are so good with high amounts of high-dimensional massive data sets, especially with unstructured data where the bare bones data like a pixel or a word doesn't really mean anything, but you can pick up these latent structures.
This kind of reminds you about that analogy where there's an elephant and different people try to touch different parts of the elephant, and then all of them kind of come together, and that's when they realize, oh, it's actually an elephant. But otherwise, they're guessing, hey, this seems to have a trunk, and then somebody's talking about the tail, and somebody's just talking about the leg.
Exactly. So no specific layer can do the entire thing. Got it. So what's deep learning versus traditional machine learning really quickly? Traditional machine learning, you have to do manual feature extraction. This is really time-consuming. You often need a certain level of expertise. For example, in computer vision, you need to know all of these algorithms for doing feature extraction before you finally feed it into a classification algorithm that can then tell you, is this a cat or a dog or something else? In deep learning, we kind of combine these middle layers. So we do feature learning and classification. So you don't really need any level of hardcore feature engineering. The neural network actually will learn to represent the data by itself. And then finally, you get the output. So this is an example of the most simple kind of neural network, a feed-forward neural network. And this is a two-layer neural network. You can see we put in input, maybe images, and you have two hidden layers before finally getting your output. So if we look into one of these, for example, you can see that we're getting an inputs from the previous layer. And in this case, we're multiplying it by a weight. So these are like the weighted inputs. And you sum that up, and you pass it through an activation function, which tells you, whether to amplify or dampen these inputs and how important they are. And then you feed that output into the next layer and so on. So you can kind of see an analogy between that and a neuron in the human brain taking in synapses and bringing in these signals and producing output. So this is another type of neural network, which is super popular in image. This is a convolutional neural network. In this case, CNNs are really good at preserving depth. So images have 3 channels for RGB. So that gets preserved, and there are a couple of important layer types that happen. So a convolutional layer will basically filter through the inputs and see which of these inputs are important. And we won't go into too much detail of the math, but that's the general idea. We have the pooling layers, which the goal of that is to kind of reduce the number of inputs to just kind of condense the information, so to make sure we're not using too much memory, to make sure we don't have too many parameters we have to train on, because that gets really expensive and time consuming. Finally, have the fully connected layer, like the network we showed previously, which will actually tell you the classification, like the probabilities of what each category will be. So really quickly, the life cycle of deep learning development process to production. You define your problem. For example, I want to categorize the objects in an image. You acquire and process data. You usually need to acquire and process a lot of data because deep neural networks excel on massive amounts of training data. So unless you're quick starting your development with a pre-trained model or something like that, you're often going to need a lot more data than you're used to for traditional machine learning. You design the model architecture, so basically the types of layers that you need, and you train the model. So training the model involves, first you initialize the weights. So the weights are what are essentially the most important part of the model that we want to train, which tell us how important to weigh each of the inputs that come in. And we feed in mini batches of data, so we train on subsets of data at a time. You don't want to train on the full data set, and it's too slow to train on only one specific data point at a time. And then you calculate the loss. So the loss is essentially your error metric. We want to see how good the model is doing. So in the most simple case, this is like the desired outcome minus the actual outcome. And we want to optimize. So we want to minimize the loss in this case. And this is where we get into computing the gradients to actually see what are the best weights that will produce the minimal amount of loss or the best accuracy. Finally, we update the weights, and then we continue the training cycle. We feed in another mini batch until we go through our data set and the number of epochs or cycles we want to run through our data set. Finally, you want to test and evaluate your model, make sure it's performing well enough for you to actually use. And then you will deploy your model so that it can be used in applications so other people can use that model. And yeah, so that's kind of the summary of the life cycle. So really quickly, what are the characteristics of deep learning? Massive amounts of training data, excels with raw unstructured data like audio files, images, text, and does automatic feature extraction or feature learning for you. Finally, it's computationally expensive because we're training on a lot of data and we're also training on complex architectures. And this is why deep learning really goes hand in hand with the use of hardware like GPUs and now even more custom hardware. So you really need that if you want to do any amount of training, reasonable training in an amount of time that isn't on the order of months, for example. So how do you actually get started? There are a ton of popular frameworks that are used for doing deep learning, a lot of libraries, TensorFlow, PyTorch, MXNet, et cetera. And there's another thing called Onyx, which we won't go too much into in this presentation, but it's a collaboration between Microsoft and Facebook and Amazon. And it's creating an interoperable representation of deep learning models so that you can interoperate between frameworks. You can train a model in TensorFlow, convert that to Onyx, and then load that into CNTK, for example. And you can run these Onyx models and target them on a variety of hardware and runtimes. So how do we actually get started on Azure with doing deep learning training?
So folks have a good idea about deep learning now, I guess? Okay. Let's switch gears now and start talking about how you can start doing deep learning in Azure. One of the easiest on-ramps into doing deep learning and AI development in Azure is the Azure Data Science Virtual Machine. And what this allows you to do is essentially it pre-configures an environment of all the rich platforms and tools that you would need for AI development in Azure so that you can get that cloud scale for free. There are samples that are preloaded on this VM itself to get you started. So if you want to, say, play around with PyTorch or with TensorFlow or with Azure Machine Learning, there are sample notebooks that can easily get you started. Double-clicking real quick on some of those preloaded tools. We have language support. We have Python, for example. We have R. We also have Julia and C#. We have a bunch of development tools. We support both VS Code and Visual Studio tools. We have Jupyter, which is a very popular tool for doing Python development in the browser. We also support open source tools. We have a Git bash installed, so you can start cloning your Git repositories. We support a bunch of integrations with the data platform and ingestion tools, such as SQL Server and Data Factory and the Azure Data Lake. We also have a single node instance of a Spark server already running on the DSVM when you spin it up. Bunch of exploration and visualization tools like Excel and Power BI. ML and AI tools. It comes preloaded with Azure Machine Learning, which we previewed this week. It also has Anaconda, and it contains multiple Conda environments. So if you are working with Python 2.7 or Python 3.5, and now we have Python 3.6 as well, all of those are pre-packaged for you, so you can use whichever Conda environment you want. And then we also have a bunch of deep learning frameworks already installed. We got PyTorch, obviously. We have TensorFlow. We put in all of the GPU drivers that you would need to use the underlying GPU infrastructure in Azure. It comes in 4 specific editions. We have something for Windows, which is the Windows 2016 DSVM. We have something for Ubuntu as well. And then there is a deep learning virtual machine, which is essentially just a bunch of more tutorials. We keep getting this question, hey, so is deep learning virtual machine the only VM where I should be doing deep learning? Should I not do it on a DSVM? That's actually not the case. You can use any of these VMs. It's just that the deep learning virtual machine is having a bunch of more notebooks for you to get started on deep learning. And then we also have a GeoVM, which is essentially containing the ArcGIS Pro software, and it has a bunch of notebooks for you to be able to use them for geospatial analytics. Some examples of applications that have been developed using the GeoVM are blight detection, for example, in a city, or being able to predict accidents using data such as the angle of the sun and how close were we to an intersection and the weather data. So why data science VMs? It's an elastic desktop for you in the cloud. You don't have to worry about having to update your GPU every once in a while or having to buy new infrastructure. You essentially just spin up a DSVM, you remote into it. We'll see if we can get to a demo of that as well. And you essentially have this pre-configured environment, and all of those tools are preloaded for you. You can start with a cheaper VM, and then you can resize it whenever you want into a more expensive one. Say when you're just playing around with data, you probably don't need a GPU. Start with something that's much cheaper, and then you kind of resize it, move to a GPU-based machine for a couple of days, and then you again scale it back down. And you get charged on a prorated basis. That's the power of the cloud. It's a pre-set-up environment. Gone are the days where people come into a classroom or they come into a new team, a data science team, and they're like, yeah, let's spend the first 2 weeks just setting up all our tools. And even after that, things don't work the same. Hey, how did you get that icon? I didn't get it. How did that library work with this particular tool? Mine didn't. And all of those things get pre-configured for you, and we guarantee the same environment. Say you want to run a workshop or a lab, and you want 50 similar environments. This is the easiest way to do that. And integrations with things like dev test labs help you assign quota policies also on it. For example, I want to shut down the VMs after the workshop is over. Or I want to ration the quota of the VMs across multiple users. All of that gets super easy for you to do. You can easily get started on Azure Machine Learning. As I said, it comes preloaded with notebooks and the SDK itself. And obviously, it's enterprise ready because it's essentially a VM in the cloud. So it's enterprise ready and globally available across all of the geos. But the best part is that it's priced the same as the base Azure VM. So whenever you're using any VM, if instead of spinning a normal VM, you spin up a DSVM, you get all of those tools for free, and you just pay for the underlying compute. There's no surcharge over it. There's no additional cost. So we talked a little bit about single node, which is a DSVM. You kind of get started. But as Meena was talking about these huge data sets and doing deep learning, you will soon realize that you need multiple nodes and you want to do some sort of distributed training. And Azure is the best place for that. We have a great platform that you could use potentially for doing distributed training on the Azure infrastructure. So let me walk you through that a little bit as well. Just recalling real quick, this is how a convolutional neural network kind of looks like. You have an image, you kind of break it down into individual layers. You have convolutional layers, pooling layers, and then the final fully connected layer. And there are multiple combinations of these layers that kind of keep occurring one after the other. There are two ways that you could try to do distributed training when you're trying to create this model. Say you have a bunch of images, there's images of cats and dogs in our example, and you're trying to create that same convolutional neural network model. You could either do data parallelism, and if I got the animations right, let's see if this works. So you could split the data such that a part of the data gets trained and a convolutional neural network model gets trained fully on that data. And then the other part gets trained separately. And then we kind of combine the outputs of that into a single model, which is essentially taking the outputs from those two workers and then getting them all together into one final output for your model. The other way you could do this actually is model parallelism, where let's see if the animations work. Perfect. So in this case, what you do is you try to use the same data across all of the worker nodes, but you split the responsibility of creating that model itself between those workers. So as you can see here, we have split the model into a first part and a second part, and we train it on the entire data set, but essentially you have two separate portions of the model being trained, and then they kind of get combined together, and we have a single model output. So those are the two ways that you could do that. But as you can imagine, there are some challenges with distributed training. Think about all the dependencies that you got to replicate, all the containers that you got to create with all of these dependencies. How do you get the same environment across all of those worker nodes? Is there an easy way to do that? How do you schedule jobs? What about job prioritization? What if somebody else had already submitted a job? How do you go distribute the infrastructure and the quota that you have across all of those jobs? How about distributing data itself? We just talked about data parallelism. How do you actually split this data in a meaningful manner so that your models can get trained? Scaling up and down resources, how do you pay only for what you're actually using? I don't want to be spinning up GPUs, pay for it all over the weekend when I didn't use it. Provisioning clusters of VMs. As we saw, there are multiple worker nodes. How do we make sure that you're able to provision them at the same time and then all of them kind of talk in tandem with each other? Gathering results. Once the models are kind of coming out, how do we ensure that all of those results get combined together and we have a meaningful output from that job? Secure access. You want to go back into the VM if something fails. You want to figure out exactly what's happening, what's the environment. Did I not install a dependency? How's the output looking? And handling failures. Of course, you want to see what kind of error logs are being generated, and is there an easy way to access them without you having to SSHing into each of those individual nodes. So this is quite a bit. How do we go solve this? We have something called Azure Batch AI, which is essentially a preview service in Azure geared towards distributed training, especially for deep learning models, and works with most popular languages, works with PyTorch, TensorFlow. We have support for Keras, Horvath, which is a distributed training framework by Uber. Supports running jobs on a VM, or you could run them in a Docker container. It can auto-scale the nodes for you. It supports both low-priority VMs. So there's this concept of low-priority VMs in Azure, where we essentially use excess capacity in Azure to give you a much better rate on using those VMs. So you can essentially say, hey, I want to only use low-priority VMs. It could happen that your job gets kicked out in case that VM is required by someone who's paying a higher rate. But more often than not, there is some intelligence built in there, and your jobs go through on these low-priority VMs. And then you can obviously use a dedicated VM as well, in which case it's obviously more reliable. And we support a bunch of VM families, including the latest GPUs for this deep learning model training. And I'll dive a little bit into those families as well real quick. So Azure has a great support of all of the different NVIDIA GPUs that we currently have. There are three specific families. Let me start with the graphics one. So we have the NV series, and this is powered by the NVIDIA M60 GPUs. This is essentially for visualization. Say, for instance, you're running AutoCAD models, or you want to kind of play around with those kind of graphics on your machine. That's where you use these GPUs. The second is the compute series, which is the NC series. And this is essentially useful where you want to do you want to scale up your training, or you want to do high performance computing. That's where the NC series kind of comes in. It's powered by three different GPUs, the K80s, the P100s, and the V100s. Those are different versions that we have launched over time. As you would imagine, the V2 series actually brought a 2 to 4x% performance improvement in computing itself over the V1 series. And then the V3 series brought in another 1.5x improvement over the V2 series. And then the third family here is the deep learning family, which is specifically geared towards the deep learning model training that you want to do. So this is the ND series. It's powered again by the NVIDIA P40s. It also has support for InfiniBand. InfiniBand is a technology which allows you to easily talk between multiple nodes. So when you are trying to run a job, you would probably need like 3 or 4 VMs. How do we make sure that all of those VMs are talking to each other so that you're able to go build a model? That essentially happens through InfiniBand, and we have support for that. The most exciting news is that we introduced 2 new GPU families. One of them is the version 2 for our graphics family. It's powered by the NVIDIA M60 in this case. And then the other more interesting thing and more relevant to our talk is the deep learning family, the NDV2s. And they are powered by the latest NVIDIA V100s. The best part about them is that they got 8 GPUs in one single VM. So that's like literally the most computing power that you could potentially get for training on a GPU. And they're connected by NVLink, which is proprietary technology and allows you to communicate much faster between the GPUs.
So yeah, now that we have a kind of good understanding of deep learning and the infrastructure required, let's take a look at how we would do it with PyTorch, which is a pretty popular deep learning framework. So what is PyTorch? It's a Python library for deep learning written in Python and C++. It's super popular, especially with researchers and in development when data scientists are developing their models. Here's some customer testimony from Andre Karpathy, one of the leading experts in computer vision today, current director of AI at Tesla. So what's so great about PyTorch if it's improving everyone's health? Let's see. So PyTorch is NumPy-like, has NumPy-like support, but for GPU-accelerated computation. So these basic building blocks are called tensors. If you're not familiar with Python, NumPy is one of the most basic and important libraries for doing data manipulation in Python. And it's basically supporting n-dimensional arrays, which are really important in deep learning, where everything is essentially matrix computation. But this gives you the power of doing computation on GPUs. So here's an example in PyTorch of just creating an array of length 3. And you can easily specify what device to put it on. In this case, we're telling it to go on the first GPU in a machine. And so the computation will happen on a GPU device. More importantly, PyTorch is a dynamic computational graph. So most deep learning frameworks are either dynamic or static-based graphs. You can think about this in the construct of define by run versus define and then run. So in a dynamic graph, your graph is, let's wait for the GIF, but yeah, a dynamic graph, your graph is computed, created on the fly. So it's really Pythonic in that anything you write will actually get compiled and run at that point. This is different from a static graph where all of the graph is first defined and then you use that graph over and over again when you feed in new input. So we can take a look at how this looks in PyTorch. So if you create x and y, which are basically scalar values 4, 4, and 6, and then you add it, you can immediately print out z and get 10. Or in this case, the tensor version of 10. You can put that to NumPy really easily with a call to NumPy. And in TensorFlow, which is a static computational graph, and probably the most popular deep learning framework out there, you create what are known as placeholders for your constants and variables. So in this case, if we print out z, we don't actually get a value. We get a placeholder for the node in the graph. So to actually run this and get a value, you have to create what is known as a session in TensorFlow and actually run this session in order to get value for your node. So you actually have to run through the computational graph. So as you can imagine, dynamic graphs are really Pythonic, and they're super easy to debug. You can debug with any of your regular Python debuggers. And because of this imperative nature, control flow is really easy, and it is as you would expect. So if you have conditional statements or while loops, for example, you can write those as you would feel like you'd write them in Python, and it's pretty intuitive. So in TensorFlow, if you wanted to do this, you would have to create, you would have to use their nodes that they actually have for representing while loops or a node for a conditional statement. And then you would actually then have to run this through a TensorFlow session. In PyTorch, You can write your while loop as you would expect, and this immediately starts running the computations and looping through this. But that isn't to say that dynamic graphs are like just completely great. As you can imagine, static graphs are really good for production level scale because they are static and the same. You can easily optimize them for running inference and for production. And likewise, static graphs have their own cons. So TensorFlow, for example, actually has what is known as TensorFlow Eager, and that allows you to use like imperative execution on TensorFlow. Finally, not finally, but PyTorch also has native ONNX support. So as we said, ONNX is an intermediate representation to operate between deep learning models. And PyTorch natively exports ONNX. So if you train your model and write it in PyTorch, with one line you can export it to ONNX. And this means that with an ONNX model, you can target any variety of hardware or runtimes that are supported. For example, NVIDIA's TensorRT or Microsoft's ONNX runtime. You can run target inferencing on any type of hardware, CPU, GPU, FPGA, for example. And also with an ONNX model, you could then load that back into another framework that supports ONNX importing, and then continue with your model there. Finally, PyTorch is going to be releasing their 1.0 version soon, and they're really focusing on production-ready support in this version. As we said, PyTorch is really good for research and prototyping, but currently not as great for production. So what Facebook is actually doing is they're combining their Caffe2 backend, which is their deep learning framework that's really lightweight, it runs really well, for example, on mobile, with the PyTorch front end so that you can still get the great Pythonic experience, but with more production level readiness. So how would we actually take a model and train it and deploy it in PyTorch, for example, using Azure Machine Learning? What makes Azure Machine Learning easier than, for example, just training on your own local box?
Thanks, Meena. So yeah, we've talked a lot about the infrastructure and then the language and then being able to actually build models and train them. But all of that is quite a lot of work. And that is where we have the power of Azure Machine Learning service to help you out and be able to create and train and deploy better models. So let me walk you real quick on how a typical lifecycle looks like and how you can simplify it using Azure Machine Learning. Quick pitch here. Azure Machine Learning is essentially a Python SDK, and it's very easy to use essentially because you can import it in your Python notebooks and then you can start using all of the power of Azure Machine Learning. And I'll walk you through some of the functionalities that we have through the slide. So any model development cycle essentially starts with preparing your data. And we have a couple of options here. You could essentially use Azure Databricks, or you could use the Azure ML data prep SDK to play around with the data, figure out exactly how it looks like, see exactly how you want to featureize it, what kind of compute you would need for that data. Do you need CPUs? Do you need GPUs? Do you need a combination of that and everything? Then you go into this experimentation phase where you essentially need some way to be able to collaborate. And that's provided by a concept called workspace in Azure Machine Learning service. And it essentially allows you to collaborate and share your resources. For example, hey, what is the kind of training data that I want to be using? What is the kind of model versions that I want to be having? And all of that is easily provided through Azure Machine Learning. As you can imagine, the compute infrastructure is also managed by Azure Machine Learning. So all that you have to do is essentially just mention whether you are going to bring your own compute or you want to create a compute from here. Just give us the VM family that you want, and we can take care of the rest for you. When you're trying to train your model, you essentially say, this is the training data that I have, and this is the compute that I want to use. And then from there on, we can go distribute your job, use Azure Batch AI as the underlying layer, and be able to run your job, training job for you. Once you have the output of a training job already with you, you can actually use that to register a model. And the best part about model management thus becomes that all of these outputs from these individual runs and from these various data scientists who are collaborating, they are in this common workspace. So if there's someone who leaves or goes on a leave, then in that case, you already have the history of what was being built, what were the dependencies through each of those models that were built, what were the kind of outputs that you saw for each of those models. You can also then go start creating an image out of that model itself, build an image, go register it in the image registry. And then from there on, you can use Azure Machine Learning to even deploy your model. And this could be either on an edge device, this could be on something like Azure Kubernetes services. And this entire end-to-end flow is essentially powered by Azure Machine Learning, simply by using simple functions that you can use in your Python notebook. So let's try to apply Azure Machine Learning and our learning of deep learning and distributed infrastructure through an example. So what we are going to talk about today is style transfer. And what it essentially does is it tries to recreate images using the style of another image. I'll try to do an animation here, and hopefully this should be self-explanatory. So we have a portrait of Mona Lisa here, and we actually try to pass it through a painting by Picasso. And this is the actual image that got output by that same deep learning model. Let's try something with Van Gogh now. This is the Starry Night by Van Gogh. And again, as you pass Mona Lisa through it, you're able to transfer the style onto that image. And similarly with the painting from Monet. So kind of explaining how you would build a style transfer model or trying to map it to our understanding of deep learning itself. You start with a content image. This is the image that you essentially are giving as input to the model. You also start with a style image. This is this image from which you want to copy the style over onto the content image. And then essentially the output is the stylized image. And when Meena talked about loss functions, you can think about the loss function in this case to be something as a combination of the content loss and the style loss. Those are the two losses that you're trying to optimize on. And you can even weight these losses. For example, if I wanted the final image to look more like Mona Lisa and less like Van Gogh, I would try to reduce the content loss more than the style loss, or the other way around. So that weighting is also very easy to do. You can essentially just play around with the weights and be able to create your own deep learning model.
Okay, yeah, so let's actually take a look of how we would do this with Azure Machine Learning. So Azure Machine Learning is really tightly integrated with Visual Studio Code. There's a Tools for AI extension. So if I go here, I can see all of my files that we're using for training. And this is going to be the main file that will actually run training. And we're not going to dive too much into the code, but as you can see, this is just for training the style transfer model. We're optimizing for this loss metric that Nishank just mentioned. And to make sure that our model can perform well on arbitrary images when we feed it into stylize, we train our model using the Cocoa data set. In this example, it's only 1 gigabyte, but there are 12 gigabyte versions of the Cocoa data set. It's just a data set of images to make sure it can do really well in arbitrary images. So we're going to use the Azure Machine Learning Python SDK from a Jupyter notebook, which is an interactive way to use Python in your browser. So there's the concept of a workspace in Azure Machine Learning, which is the high-level resource that manages all of your other resources, such as data storage and your compute clusters, for example. So in this case, we've already created a workspace, so we're just instantiating that. You need to have a subscription ID and a resource group, and you can create your workspace. Then we're going to create a remote compute target. It's really easy to provision a cluster from your Jupyter notebook or from your Python script. Let's say we want to provision a CPU cluster. You just specify your SKU over here. In this case, it's a standard D2 V2 machine. So we're going to provision the CPU cluster, and we can kind of wait to see what the output is looking like.
And as you can see here, you can provide a bunch of parameters also to the compute you're trying to create. In this case, Meena has autoscale enabled equal to true, and she gave a min node and a max node. And what that allows us to do is you basically start with a 0-node cluster, and you're not paying for any compute. We provision the compute for you, but it's just sitting idle. And it's only when you submit a job on that compute, that's when it autoscales to 2 nodes, runs the job, and then scales back down to 0. So you can kind of think of it as a way where you use that compute only for running the job and not otherwise. And that reduces your cost.
Yeah, so while we're waiting for this to provision, we can take a look at the VS Code Tools for AI extension. So you can see, you can get access to your subscription ID right over here in your workspaces. So this is the workspace I'm using. And then within this, you can get access to all of your experiments, which encapsulate the training runs you're doing for a specific problem, your compute. So for example, these are all the experiments that we've tested. And everything right now is under an experiment for style transfer. And you can see all of the compute clusters we have. Finally, when we go to deploy the model, all of that gets managed by model management. So this all gets versioned, so you can easily do A/B testing of your models when you deploy a web service, for example. You can get all the images that we're going to use to deploy. And then finally, you can get the service that you actually need. Yeah. So let's see if, OK, great.
Yeah. Sorry, on that, when you said you can go through the deployment history, can you actually do the versions from there, from VS Code? Or do you have to actually go out and stay in the workspace?
Sorry, what?
If you want to look at a model's version history, like when you're managing, can you see like?
Yeah, oh, so the model is identified by a name and a version number. Yeah, exactly. Okay. So if I've named the model Picasso, but I've like deployed it, registered it like 3 times, it goes like that, yeah.
We have another question, Meena.
Yeah.
Is there also special support for model checkpointing? I mean, I'm training the same model, but during training, I'm checkpointing it, and at the end, I would like to post the
Exactly, yeah.
under one model and not like a bunch of different.
So the question was, is there support for model checkpointing? This is when you checkpoint during training, and then, for example, if your training stops suddenly or you need to go back later, you don't want to start training from 0 again from your uninitialized weights, so you want to start from where you left off. So right now to do that, this is one of the features we're working on. We're currently in public preview, but for GA, we want to make this as seamless as possible. But for what you can do right now is in Azure Machine Learning, as we'll see, the outputs folder, anything you output to an outputs folder gets picked up and saved to your run history. So you can actually download, if you output your checkpoints to that folder, you can download all of those files. And then when you're starting your next training job, you can upload that to your workspace's data store and then easily access it from there. But we are working on making that even more streamlined. So as you can see, we provision our cluster straight from here. This is a CPU cluster. We want to use a GPU cluster for training. So we've already created a GPU cluster, and we can just get that as our compute target. So the training data we're going to be using is the Cocoa data set. These are just a bunch of random images. Here are some of the files. And a workspace has a concept of a default data store. And data store is an abstraction over Azure storage, such as Azure File Share or Azure Blob Storage, and support is coming for Azure Data Lake. And if you don't have your blob storage account already created and configured, and you just want to use the workspace's default one, you can easily do that. Or else you can register your own personal Azure storage. So in this case, we're getting our workspace's default data store. And we've already uploaded the data set, because it was like 1 gigabyte, and into a folder called Cocoa at the root of our data store. So we actually want to specify the path to that folder so we can pass it into our script. Now let's actually train a model on a stylized image. So here is a painting from the series of Picasso's Les Femmes d'Alger. I think the last series of this paintings auctioned off for like $180 million. So now let's create an experiment. So,
are you saying that we can create an image out of that?
Yeah, I'll create you the same painting, but for free.
That's awesome.
So now we're going to pick an experiment, and this experiment actually will encapsulate, all of the runs that we want to do. And then finally, we actually want to train this model, and we want to train it distributed. So in our training script, we've actually used Horovod, which is a distributed training framework from Uber that Azure Machine Learning supports. So it's really easy to wrap your single node training code into using distributed training. So in Azure Machine Learning, we have high-level abstractions for deep learning frameworks, such as PyTorch and TensorFlow. So in this case, we just specify all of the script parameters. So these are the command line arguments to our training script. As you can see over here, we're passing in the reference to our data path on our data store. And we're passing in the style image. And here is where we're saving the model outputs so that we can actually access it later, or else it'll be hard to do so and get that from our remote VMs. We're going to train on 2 epochs, so 2 cycles through our Cocoa data set. And we're going to run it on GPU. So to do distributed training, normally you have to configure your own cluster and manage and figure out how to run your script on each of these nodes. But in Azure Machine Learning, it's super easy. You just instantiate this PyTorch object, and what it does is you specify the project folder where all of your training code is contained, and then you pass in your script parameters, the compute target that you want to run on, and you specify the number of nodes. In this case, we want to do distributed training on 4 nodes, across 4 nodes, with 1 worker per node, so we're going to utilize each of the nodes' GPUs. And we're going to train this with the Horvath framework, which uses MPI, so we just specify that as our backend. And then finally, we want to use the GPU. So we've started the runoff because it takes like 10 minutes or so to get started. But as you can see, this is submitting the run so that it starts running on your remote compute target. And we have this really handy Jupyter widget because our goal is to be really tightly integrated with Jupyter notebooks. So you can actually visualize how the outputs of your run, and this will give you the outputs on the chief worker node. And we'll wait for this to get started, but we can actually see the output of a previous run. So over here, as you can see, we're streaming all of the logs from the output. We're training, this one was on like 5 epochs. And you can actually visualize how your run is doing if you instrument your training script with logging to Azure Run metrics. So in this case, we were looking at across the average content loss, the style loss, and then the aggregated total loss. And we can see how this is doing across the epochs and mini batches of our training data. So once you've actually finished training your model, it's really easy to get that model back. So if you look at all of the models that Azure Machine Learning picks up, the one that's important is the one in the outputs folder over here. So this is our PyTorch trained model. And we can easily download that model to our local machine or immediately register it if you want to use it straight for deployment. And to actually deploy a model, it's also really easy to do this from a Jupyter notebook. We're not going to run it right now, but we deployed a service right before the session. So you create a YAML file which specifies all of the things you need in your environment. So this is like all of the packages that your script uses, any other dependencies. And then you specify the container image. So this includes all the files you'll need. This is like the script. We have what is called a scoring script, and this is what actually you provide to Azure Machine Learning, and it has all the logic for initializing your model and how to actually run predictions on that model. So over here, we can take a quick look at the training script. So in Azure Machine Learning, your scoring script needs to have 2 functions. This is an init function where you are actually loading in your model. And when we go to deploy the service, we're actually going to specify the model to register. And so you can get the path to that model using this Azure Machine Learning function. You load in your model, and then you specify the run method, which is the one that tells you how to actually predict on your data. So if we wanted to deploy this as a REST endpoint, then in this case, we're going to send in inputs and send in images and get back images encoded in base64 serialized strings. And so we'll actually get back the stylized image.
And Meena, can you use Azure Machine Learning on the portal also?
Yeah, so you can also use Azure Machine Learning through the Azure portal. And this is a really good way to visualize things after you've already done the runs and you've long gone rid of your notebook or replaced it with something else. So this is the visualization of everything in our PyTorch style transfer experiment. You can see how many of your runs completed, how many failed, if you had any errors, how long the duration of each of these runs are, and you can actually dive into one of them. So you can take a look at this run that we ran previously, and you can actually visualize, once again, all of the graphs, all of the metrics that you've logged. You can get details, and you can actually also see the various other resources in your workspace, such as the compute, the models. So we offer a lot of integration with Azure Machine Learning. So if your preference is IDEs, you can do that. If your preference is accessing these visualizations and information in the browser, you can also do that too through your Azure portal, and all of your workspaces are visible from there. So let's actually see like how we would, let's actually finish deploying this model. So after you've configured your container image, you also want to configure your ACI web service. This is just like the number of CPU cores in memory. In most cases, like 1 core and 1 gigabyte of memory are more than enough for your job, so we'll do that here. And then finally, we'll deploy the web service. So you give the service a name, and you specify all your configurations. And here, you specify the path to your local machine where your model is. And then finally, you're deploying your service, and we'll give you back a REST endpoint. So let's see if we can actually take a look at using our service in action. We have a service that's already deployed that we can use. So over here, what we're going to do is, Nishank, I went to come take a picture of you, so let's pull up.
This is the most exciting part. I've been
camera.
waiting for it for so long now. Yeah. Finally, someone's going to make me beautiful. And I don't need to pay for it, at least not $180 million.
Okay. Oops.
Oh, no. I am not going to look beautiful.
So we're going to save this. Let's save this image as Nishank. And let's go back to our web service. So we're still doing all of this from our Jupyter notebook. And
can you keep the style more than the content for this one, please?
we'll see. This model's already trained, so
Okay.
you're out of luck. But okay, so now let's get our service back. We know the name of our service. You could also use the endpoint itself. In this case, we've previously deployed the service. We're going to convert our image to a, let's put it in, base64 encoded string. And let's take a look at Nishank in our Jupyter notebook. And now let's actually evaluate, stylize your image. So if you can see here, we have, so in this case, we were testing this locally, but we actually want to run this. So service has a run function, and this is where you pass in your data. And this is going to take maybe like 8 seconds or so. So if you want to get faster inferencing, you can either inference on a GPU. Oops, it's not good.
I knew there was something that's going to be wrong because of my photo.
Okay. Okay, let's just see how we can do it from our local model that we deployed and that we trained and downloaded. So this is, going to take about 8 seconds or so. So if you want it to go faster, you can also make the image smaller. So make the content image smaller, like decrease the dimensions of that.
Or use the power of the cloud to make it faster.
Exactly. So let's actually display the image that got saved. So this is Nishank.
Oh, this is not bad.
And you can see it's kind of getting the textures and colors of the original image. So if we wanted even more of that style, we could amp up the style weight, and we could tune these hyperparameters. There's a handy other feature in Azure Machine Learning called, that's the hyperparameter optimization feature, and it'll actually help manage and try out different hyperparameters for you. So yeah, this is an example of Nishank, and I'll Venmo charge you for 180 mil after the session. But as you can see, we've been able to do all of this from data prep, training to deployment, all from our Jupyter notebook. We could have also done that from VS Code with the tools for AI integration. And you can visualize all of this in all of these places or the Azure portal.
You want to show the data science virtual machine also real quick?
Yeah, sure. So we have some time. Nishank, if you want to show how to provision that.
So we gave you a quick overview of the DSVM as well. I just want to show you folks how you can actually spin up a DSVM real quick. Go to the Azure portal, try creating a resource. Just search for the Data Science Virtual Machine. 1 second, type. And it'll start showing you all the SKUs that we support. So in this case, I'm going to choose a Windows 2016 SKU. And it lists out some of the tools that we offer. I click on Create, and it's now going to get into a simple VM creation flow. It's exactly like how you would be spinning up a VM in Azure. You go through this, you kind of name it, say, test demo. And one of the best parts is that it allows you to choose a size. And now you can use these smart filters to actually decide on exactly what kind of machine do you want. So for example, if you want something that has a GPU, you essentially just say, hey, I'm only looking for SKUs that have a GPU. There's obviously no size :small in this case, but if I can get these to work, then we should be good. Okay. So yeah, I just switched back to the general purpose VMs, but you can essentially see how we kind of give you a rough cost. We keep getting this question, so is this the amount of money that I got to pay? But this is all prorated, so if you use it for like say 10 minutes, it's going to be a few cents, for example. And then you can choose between these VMs. You say, hey, I want a specific SKU, and then from there on, you can essentially just spin up that particular VM. And it'll be spun up with that, with all of those configurations for you. So I can just simply click on Review and Create, and it's going to spin up a new VM. I think we might be out of quota.
Yeah.
Yeah?
Yeah,
Okay.
but anyways,
Yeah.
you can do this with an Azure subscription, and if you want to use the free trial with free credits, you can do so. So let's just quickly recap what Azure Machine Learning is doing. So we really want to make sure that the transition from training on your local machine, that's where a lot of data scientists will start, to scaling out on the cloud is as easy and painless as possible. So when we go to train and submit the job, Azure Machine Learning snapshots a folder of all of your training code and all of the code dependencies and sends it to your experiment. The experiment will create a Docker image. So in the case for PyTorch, because we provide a high-level abstraction, we already create the Docker images for you with the latest stable versions of PyTorch. If you're using GPU, it includes the PyTorch GPU version, all the GPU drivers, any of the other packages that you would need to do distributed training, in this case, Horovod. Then you deploy the Docker and snapshot this to the compute target. And this is where we're actually going to run on the remote VMs, in this case, our remote GPU VMs. And we're also going to mount our data store to compute. So I forgot to mention, but in our previous example, what we were actually doing was we were mounting our data store to each of our remote VMs, so we don't have to deal with uploading and downloading like 1 gigabyte of data or more every single time to each of these machines, especially if we know that we're going to have to iterate. So it's not like we're going to do one distributed training job and be done with our experiment.
And just to call out, there are multiple compute targets that Azure Machine Learning supports. You can use batch AI for distributed training. You can also use a single remote VM. We also support AKS. And you can also bring in your own HD Insights cluster if you want and just attach it.
Yeah, and so once you've done that, it'll launch the script, it'll train your job, and it'll stream your outputs back to your experiment. So if you're looking at this in a Jupyter widget, you can stream all of those outputs back. And as we said, anything that gets outputted to a folder named outputs or logs gets picked up and saved for you to your experiment's run history so that you can look at it later or download those files. And yeah, so you can stream all of that information back to your local machine where you're, for example, in our case, running your Jupyter notebook.
And all of those logs also show up in the Azure portal itself. So you can either use your own notebook, we have widgets supported there, or you could use it in the portal itself.
Yeah, and so we just wanted to show you how streamlined it is to do everything for a full life cycle from end-to-end training to deployment. And for more information on the Azure Machine Learning service, which we announced our public preview refresh this week, there are all of these sessions that happened earlier this week. So if you're interested, you can go back and take a look at those recordings. So finally, we just want to say it's easy to do deep learning on Azure, and it's easy to get started. Even if you're not really familiar or you don't have the compute yourself, you can easily leverage the power of Azure and do so. So these are links for some more information on the things we talked about today: Azure Machine Learning, the Data Science Virtual Machine, PyTorch, the framework itself, and Onyx. And finally, if you have questions, feel free to email either Nishank or me at our email addresses here, or reach out to us after the talk. Thanks so much.
Yeah, and do rate our talk and also have a safe flight back, please. Thank you.